Okay, YouTube, in my last video we confronted how to solve absolute value equations, and in this video we're going to look at solving absolute value inequalities. Of course, we mean inequalities are things including like less than, greater than, less than or equal to, greater than or equal to, and not equal signs, okay? So when you have an inequality involving absolute value, we're going to treat it very, very much the same way we treated an absolute value equation, which was, recall, if you had the absolute value of x equal to some constant, where, by the way, this constant is not negative, we said we could rewrite this two different ways. And what our method was basically this. We say, well, then x equals c. I mean, it stayed pretty normal as we've got it written here, just doesn't have the absolute value bars. And then the second way we rewrote it was x equals, but on the right side we made the right side value negative. Okay, so here's the deal. When we rewrite this into a compound inequality, recall that a compound inequality is just a couple of simple inequalities. What we're going to do is this. We're going to rewrite it so that we still have x on the left and 7 on the right, okay, in the first one. And then on the second one we have x on the left but negative 7 on the right. Now you notice that I didn't fill in the middle here, and the reason why is because what I want to do is I want to kind of really point out that in the first instance when you rewrite it, you're not going to change anything. As a matter of fact, let's make a little note here. This is the same as what I started with. As a matter of fact, also, the absolute value bars are the only things that are missing. But on the right side here, when we rewrote it the second time, you notice that we made the right side negative. We also actually have to take responsibility for switching this inequality sign around. This has to be switched. Okay, so let's make a little note here. Switch inequality sign. INEQ sign. Okay? And that's really important that we do that, otherwise our solutions are going to be incorrect. So when we graph this, as a matter of fact, we could just say, well, 0 is right here. It looks like we have positive 7 and negative 7, so I'll go 1, 2, 3, 4, 5, 6, 7. We're going to go ahead and put an open dot on positive 7 because it's not an or equal to situation, and label this, and we say x is less than 7. So I noticed that this would shade to the left. Now I'm going to hold off on that for a second because I also want to graph this one here. Let's take a look. It would be 7 units to the left with an open dot. I'm going to go ahead and label these things here. This is a 5, that's negative 5, this is negative 7. We're going to put an open dot on this, and it would shade actually to the right when you think about its solutions. So the interesting thing about this is when you look at this graph, okay, we'll notice that we've seen situations like this before with compound inequalities, and that these shade together. So the important thing to note here with shading together things, first of all, is that this is an AND situation. Okay, it is an AND situation. The reason why is because we could have taken these inequalities. We had x is less than 7, and we have x is greater than negative 7. If we were to like take this here, and what if I were to set it down on the other side here? You would see this. You say x is greater than negative 7. Actually, let's do this. I mean to do this first. Let's go ahead and take these two values and switch them around. We're allowed to do this in an inequality. So this would say negative 7, and we'll switch the inequality sign is less than x, because x is greater than negative 7. So this right here, and if I were to take this statement now, I guess is what I mean to say, and put it down over here, you notice that we already have x on the left, and we could just say is less than 7. So in terms of an AND situation, we say, well, this is an AND situation because I could have said x is, negative 7 is less than x, and x is less than 7, or x is greater than negative 7 and less than 7, but it is a trapped situation. So, we could say sandwiched. I use this one in class sometimes. Sandwiched in between the two values that we solve for. So, if that's all we have to do with absolute value inequalities, I'm going to go ahead and go through this spiel really quickly up here, and then we'll go through some quick examples. But it says the inequality. Now, you notice here I have the inequality of ax plus b, all in the absolute value bars here, is less than c. And we say c, by the way, we should say is greater than or equal to 0. But we say non-negative, okay? Well, if this is the case, and this is what we have on the left, then we say ax plus b is between negative c and c. Okay? So essentially what we're saying here is this. Whenever your absolute value bars are in a less than situation, what we're going to get is this. It is between negative c and c. And we've interpreted this before as being equivalent to this compound statement. So ax plus b is between negative c and c. And we refer to these as AND statements. We also say this about this here. We say always have graphs that shade towards some converging solutions, or things that make it true tend to be trapped between two values. They shade together. Okay. Now the other instance that we haven't looked at yet, you notice that this first example here was absolute value is less than. Okay, so we had implied an and situation. We didn't look at a greater than situation, but let's say we had that. What if the absolute value of ax plus b and, well, I guess what I mean to say here is greater than. So let's make this fix here. But we say where c is greater than 0, we say that ax plus b is beyond negative c and beyond positive c. So it's kind of like, you know, when you look at a real number line situation, you say, well, here's positive c and here's negative c. We're saying beyond each. We're going outward. Okay, this would be like an or situation. So we'd say this would be equivalent to, well, our original statement is, and this should be greater than, sorry. Ooh, that would be less than right there. The original statement, when we rewrite it the exact same way, would be this one here. We say ax plus b is greater than c. Okay, got that one right. But in the second statement, you notice that we say ax plus b, and we switch the inequality sign to less than here. And we call the right side negative c, just like we were doing previously. So we refer to these, of course, as or statements, and we say that they shade towards diverging solution sets. They go away. So let's solve some of these, and you're going to notice that on all of these, I mean, we break it down into steps a lot of the time, and first step in solving absolute value anything is to get the absolute value thing isolated on one side. So I do want to point this out here. This first example here, what if I were to put like a 2 in front? Okay, 2 times the absolute value of this. Well, I can't distribute, by the way, that's against the rules with absolute value, but I can do this. I could say we could divide by 2, and actually that would have been necessary before I rewrite, but I'll tell you what, we don't need to do that, so we're going to do this. It says solve the following absolute value inequalities and graph their solution sets on the number line, but also this, also tell whether they represent an or inequality or an and inequality. Okay, so when I look at this and I say less than, right off the bat, I'm going to go back up here. I'm going to say less than. Less than was this top one here, and I know that less than means sandwiched or trapped. We saw that. So this is an and type of situation. We'll see that with the graph here. But we want to go ahead and rewrite this 2 different ways. So we say 2x plus 7 is less than 11. So you'll notice that I didn't change a darn thing about this. It's the same. But I also get 2x plus 7 is greater than and negative 11. Okay, that's what we have to do in this instance. So we're going to go ahead and do what we've done in the past, which is operate the same way on all of these. So I'm going to subtract 7 from each. And I get this, 2x is greater than negative 18. And on the left side here, we say 2x is less than 11 minus 7 is 4. So now if I divide by 2, everywhere, we get this. I'm going to have to write down here. Sorry, we say x on the left is less than 4 divided by 2 is 2. Now I don't need to switch this inequality sign because we didn't divide by a negative. And same thing over here. We'd say, well, I got x, and this is, this is x is greater than negative 18 divided by 2 is a negative 9. So our and statement here, if we were to graph this, and you have to forgive my number line because I have to write on top some of these numbers here. We say 0. We say negative 9, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we say this is negative 10. Then we'll call this one negative 9. That gets an open dot, and we are shading this time. We say x is greater than negative 9. So we're shading towards the right, and then we say this is 2. On 2, we have an open dot right here, and we say it would shade toward the left. So our solution set is this and inequality here. And really quickly, I just want to see one or inequality. What if we were to come over here, and you'll notice off the bat we have like greater than. Absolute value is greater than some positive value. Again, we're going to go ahead and rewrite this 2 ways. We have 3x minus 2 is greater than or equal to 8. Again, you know, nothing changed. We say 3x minus 2 is less than or equal to negative 8. So here we go. We say add 2 to everybody. I'm going to leave these last 2 examples down here for the viewer. So we say, all right, 3x greater than or equal to 10. In this case, we get this here. We say 3x less than or equal to negative 6. And again, dividing now is a 2-step inequality, rather, I almost said equation. It's this guy here. And then we say, all right, dividing by 3 here. Divide by 3, divide by 3. We get x is greater than or equal to 10 thirds. Okay, so this is really important when we graph this. Why don't I graph this one down here? You can graph on your own paper otherwise, but we say, all right, 0. And I'll go 2 to the left, 1, 2, negative 2. This gets a closed dot, and I say x is greater than 10 thirds. And of course, 10 thirds is the same thing as 3 with 1 left over. So 3 and 1/3. So 1, 2, 3, 4. We'll call this 5. And so if this is 1, 2, 3 right here, a third of the way there, we'd say be about right there. And of course, we're going to label this so it doesn't matter. We say that's, of course, 10 thirds. And we are going to shade which way? Well, if x is less than or equal to negative 2, it would shade outward. And we say if x is greater than or equal to 10 thirds positive, we say it was going to shade this way. Okay, so this is definitely an or situation. Of course, we could label these sections of the graph as well, just like we could have done up on this portion here. But that's how you deal with absolute value inequalities. Cheers.